One key application that we can use binomial expansion for is looking at the approximation of numbers. Now, if you think back to when you did sequences and series and recurrence relations at higher, they would always take the same format. U of n plus 1 equals a un plus d. Now, in this sort of setup here, this value of a was what you looked at to determine if there was a limit. Now, if a was between -1 and 1, we were able to find a limit of the function. The reason being that if you took a to the power of n, as n tended towards infinity, a to the n tends towards 0. So what's going to happen is the curve, if you were to plot a curve of that recurrence relation, it would eventually level out at some value because your a would negate the input that the au to the n would have, the bigger that the n got. Now we can actually use this fact to be able to approximate numbers using a binomial expansion, because what we're able to do is if we can split a number up into two parts, one where there's a whole number and one where there's a decimal, as the value of the power of that decimal increases, the size of the decimal is going to decrease, so it's going to get smaller and smaller, and actually it's going to have the same logic as this. It's going to tend towards a limit, and we're going to get an approximate value for the overall value of the entire function or the entire setup. So what we're going to do is we're going to look at this. Now, that's a lot of words to throw at you. So what I'm actually going to do is show you this, show you what I mean through the use of a couple of examples. So, first one I'm going to look at is calculating 1.02 to the power of 3 correct to 3 decimal places. Now, nice calculator paper, you could very easily stick this into a calculator, job done. At this level, it's not quite as easy as that. We have to come up with a mathematical way to do it and show that we know how to do it. Well, this is where binomial expansion comes into play. Now remember that the general format for a binomial expansion is x plus y to the power of n. So what we have to do is figure out a way to write the 1.02 in the format of x plus y, then the n would be 3, and we can expand it like that. Well, 1.02, if I split that up into a whole number and a decimal number part, is the equivalent of 1 plus 0.02. I can then put that in a bracket to the power of 3, and I'd still get the same answer ultimately if I plugged it in a calculator. But now I have it written in the format that I can use a binomial expansion, because here I could quite simply say that the x would equate to the 1 and the y would equate to the 0.02. My n would still be 3, so the power wouldn't change. It's just that I now have an x and a y, and I could use the binomial expansion. So let's do that. The coefficients have still got the same, so I still get a 3, 0. This is going to be times 1 cubed. I've then got plus 3, 1. That's then going to be times 1 squared times 0.02. Then I'm going to get my next one, which is going to be 3, 2. That's going to be times 1 times the 0.02 squared. Then my final term is going to be given by 3, 3 times 0.02 cubed. So what I can now do is calculate each of those values, stick it all together, and see how I can round it to 3 decimal places. Now, one key thing to remember, if I am rounding to 3 decimal places, I only need 4 decimal places overall, because that 4th decimal place tells me about how to round it. Make your life a bit easier. There will be some calculations, like the one I'm going to show you in a minute, where you're going to get to a point that calculating the values will actually add nothing to the overall answer at the very end, because you'll end up with numbers that are beyond the decimal places you need, so they won't even be involved in the rounding. So sometimes you can actually work out the entire answer by ignoring certain parts of the expansion. In this case, what I'm going to do is each of the terms here, and I'll show you what I mean. So first one, 3, 0 times 1 cubed, just gives me 1. If I then do 3, 1 times 1 squared times 0.02, what I end up getting for that is 0.06. I'm then going to get the next term here, 32 times 1 times 0.02 squared. That gives me plus 0.0012. And then my final term is going to be given by 0. Then I've got 5 zeros, and then an 8. Now remember, I said 3 decimal places is what we're after. We only want to go up to 4 then. So this one here goes up to 4, great. If I cut this one off at 4 decimal places, my next digit's a 0, so this one is not going to add anything to my final calculation. So I can actually now just ignore this whole term here and don't even have to worry about adding it in. So I could just add these first 3 terms together and still be able to get my approximate value. So if I do that, I get 1 point, well, I'm then going to get 0.612. So 1.0612 by adding these together, rounding it to 3 decimal places, cut off at the 2, I end up getting 1.061 to 3 decimal places. Now if you stick that in a calculator, 1.02 to the power of 3, plug it in a calculator, what you'll end up getting if you round it to 3 decimal places is 1.061. So we've actually used this quite effectively to approximate that value, and if we then had extra calculations to do with it afterwards, we could work on it from there. Now that's if it's bigger than 1. What though if it's less than 1? What about if it's a value that's 0 point something? Let's imagine I want to calculate 0.9 to the power of 7 correct to 2 decimal places. I've got to think how I'd approach this one. Now I still want to use a binomial expansion. So I still want to use x plus y to the power of n. I still want to use that same format. But I still want one of them to be the whole value 1. So I've got to figure out how I can do 1 plus or minus something to get 0.9. Well, if I do 1 take away 0.1, that gives me the value of 0.9. So I can then do 1 take away 0.1 to the power of 7, and if I plug that in the calculator, I'd still get the same as that. But remember, for binomial expansion, it's got to be a plus in the middle, so I'd have to rewrite that as 1 plus negative 0.1 to the power of 7. Now it's in the format I want, I can actually use a binomial expansion on it, and then take it from there, and be able to get my final overall value. So, I look at this and I have to equate up the x and the y and the n to figure out what goes in each part, but that's quite straightforward. I know my x is going to go to 1, I know my y is going to become the negative 0.1, watch that, it's a negative value, and my n is going to be the 7. So what I can now do is start expanding it the way I want and then see how we go from there. So I'm going to do my first term, still going to be given by the same set of binomial coefficients. So I get 7, 0. That's then going to be times 1 to the power of 7. I'm then going to get plus 7, 1 times 1 to the power of 6 times my negative 0.1. My third term is then going to be plus 7, 2 times 1 to the power of 5 times negative 0.1 squared. Then I'm going to get plus 7, 3 times 1 to the power of 4 times negative 0.1 cubed. And then my next term is going to be given by 7, 4 times 1 cubed times my negative 0.1 to the power of 4. Now, if we think about it from here, we want 2 decimal places, which means that for the rounding to be effective, I have to get to 3 decimal places overall. I have to be able to get to that third decimal place. If I do 0.1 to the power of 5, what I'm going to get is my first number for that one in the 4th decimal place. So what's going to happen is that's going to have no overall effect on the rounding of my final answer. So see at this point here, the 7, 4, I can actually just do my dots to show there's further calculations that could happen, but stop doing the calculation here. The rest of it's going to contribute nothing to my overall answer, so there's no point in me wasting my time doing it when it can be used more effectively to do the first part of the calculation. So what I then do is do each step on its own and see how I go. So I end up getting 1 for the first term. My 7 gives me 7. And I've then got 1 to 6, which is just 1, times negative 0.1. So it's then going to be 1, take away 7, times 0.1. This one here, 7 2 is going to be 21. And I've got negative 0.1 squared. Now that's the equivalent of 0.1 squared, because the negative will go away. So that's then plus 21 times 0.1 squared. My next term, 7 3 is going to be 35, and it's negative 0.1 cubed. So that's then the equivalent of take away 35 times the 0.1 cubed. Negative 0.1 to the 4, so even power, the negative disappears. So I then get plus 35 times 0.1 to the power of 4. And like I say, everything beyond that doesn't contribute to the overall rounding and the overall answer, so I don't need to worry about calculating it. Do every single term here, add it all together, see how you get on. So what I then end up getting is I get 1, take away 0.7, plus 0.21, take away 0.035, I then get plus 0.0035. And as I said, there's more beyond that, but let's just focus on this first little bit to begin with. If I then add all of that up and round it to 2 decimal places, what I end up getting is 0.48 to 2 decimal places. So there you go. I've got my approximation to 0.9 to the power of 7. It's 0.48 to 2 decimal places. If you plug 0.9 to the 7 into a calculator and rounded it, that is the answer you would get. So we can use the binomial expansion to make our life a bit easier when it comes to approximating these numbers by using the facts I told you earlier on. We have to approach it in this manner. We have to have it as written as x plus y to a power, whether that's 1 plus something or minus something. We then expand it, and like I said before, if you go to a point where further expansions and further terms won't contribute to your overall rounding at the end, don't worry about it. Leave them off, save yourself a bit of time and effort, and focus on the parts that will actually have an effect on your final answer and your overall result to the question.